Okay, good morning. So let me remind you what we were doing last time. We were dealing with open and closed sets. Okay, where was this thing? Yeah, and this was the proposition we stated. The union of a family of open sets is open. The intersection of a family of closed sets is closed. Uh, okay. The intersection of closed sets uh, is closed, and the union of finitely many closed sets is closed. I think we did uh, part A last time. For part B, we have to be a little bit careful. As I said, uh, it is not true that. Oh, okay. Part B is easy. Part C, we have to be some, you know, pay some attention. Part B is easy. Okay, so we basically actually repeat part A. How? Uh, let you know. Let's say A alpha. Okay, be a family of closed subsets of X. Well, then U alpha, which is defined to be as the complement of A alpha, right? These are the complements of closed sets, so they are open, uh, are all open for all alpha. Let's say an index set. But this means what? Now by part A, uh, union of this U alphas is open because uh, any family of any union of a family of open sets is open. So I have open sets. Their union is trivially open. It's open. Hence, we see this. The intersection of A alphas. What is this intersection? This is X minus U alpha, right? Because U is defined to be the complement of A, therefore A is the complement of U. But this intersection is equal to what? This is just X minus the union of U alphas, right? Sorry, the union. However, this is open by part A, therefore this is closed. Since this is open. Okay, therefore the intersection of a family of closed sets is closed. Okay, do you have any question about this? For part C, we have to be a little bit careful. The intersection of only finitely many open sets is open, okay? Not families. In general, intersection of a family of open sets may not be open, but if you have only finitely many, then the intersection will be open. Alright, so let U1, UN be open subsets of XT. Well, then, and so take any X in the intersection. I want to show that this intersection is open. Therefore, I have to find a ball around X so that the ball lies inside the intersection. In other words, the ball should lie inside each UI. How can I do this? Well, you see, suppose this is U1 and this is U2. Okay. And suppose you have a point here, some point X, okay, like this one. Then, since each U alpha is open, of course, you can find a ball that lies inside each of them. So for U1, I can find a ball of this radius, which lies in U1. For U2, I can find a ball that lies inside U2. But as you see from this picture, the ball I choose that lies inside U1 may not lie in U2. Therefore, what we have to do, we have to just take you know the minimum of all the balls. That ball will lie inside all of them. So that's the strategy. So let me write down what I mean. Okay, since X is in UI, right? Because it is in the intersection, there is, and of course, UI is okay, and UI is open. There is some Ri positive so that the ball with center X and radius Ri lies in UI. Okay. This is true for all I from 1 up to n. Okay, these are just concentric balls, right? One of them is like this with radius r, let's say 1. This is, let's say, r5, r3, and so on. Okay, some balls. I want a radius that lies inside each UI. Well, the logical thing to do is to choose the smallest radius, right? So that's what are we going to do. Let R to be the minimum of R1, Rn. Okay. Then R is less than Ri for all I, and thus Bxr, since the radius is less than Ri, this ball will lie inside here and this will lie here for all I, but this means what? Since it lies in all of them, thus this ball lies inside the intersection. Okay, and this finishes the proof. Why is that? You see, I started with a point in the intersection. We found some positive number. Here R is of course positive because it is the minimum of finitely many elements, right? I should uh, note that, right? This is positive, and that ball with positive radius lies inside this intersection. Hence, this intersection is open, so that is open. Okay, let me ask you a question. Why this proof wouldn't work if I had not finitely many U alphas, but infinitely many U alphas? Right? Suppose that I have U1, U2, U2, U3, U5, 4, 5, and so on till infinity. Why this proof wouldn't work in that case? Do you have an idea? Yeah, right. Uh, in that case, we had infinitely many positive real numbers, radiuses, and we had to take the infimum or minimum, but minimum wouldn't exist, infimum would exist. However, infimum could be zero, and that wouldn't work for us, right? We had to take infimum of infinitely many positive real numbers, but infimum could be zero, right? Suppose Ri is just 1 over n, Rn is just 1 over n. The infimum of 1 over n would be just 0, and that would be useless, right? We couldn't find a positive radius around x that lies inside all of the balls. So that's the point where the proof would break, okay? Uh, Therefore, this holds only for uh, finitely many intersections. All right. Part D is the dual of this statement, as part B is the dual of part A. So this time I take finitely many closed sets. So let A1, AN be closed subsets of X, right? So let's see. Let's recall the statement. Okay, too far. The union of finitely many closed sets is closed. Okay, so I have closed sets finitely many. So aim is what? Uh, Show that A1, A, and this union is closed. But this is again just similar to part B. We will just take complements and work with the complements. So as before, let ui to be x minus, I'm sorry, x minus ai. Then ui is open. Since ai is closed, hence, thus the intersection u1 intersection sorry, not intersection, union, UN. What is this? This is I from 1 to n, x minus, okay, first let me write AI. This is union I from 1 to n, x minus ui, because ui is the complement of AI, therefore AI is the complement of ui, and this intersection union becomes intersection as follows: x minus the intersection I from 1 to n ui, and by part C, this intersection is closed. Sorry, open, where this is open by part C. Since this is open, x minus that gadget will be closed. Hence, this is closed. Okay. So this finishes the proof. Let me uh, state the following remark. Our proof didn't work for arbitrary unions of closed sets and arbitrary intersections of open sets. And there is a good reason why our proofs, didn't work, because they are not true. And here are some counterexamples. So let, for example, UI to be the open set minus 1 over n plus 1 over n. Okay, and from 1 to till infinity, u and let's say clearly each un is open. Okay, open. However, what is the intersection of UNs? And from 1 to infinity, well, this is the intersection of these intervals. What would be the intersection? So I am looking for real numbers that lies between minus 1 over n plus 1 over n for all n. Well, there is only one such real number, and this is just 0. So it's just a singleton, and this singleton is not open, right? Why is not open, this set? I said it is not open. Is it obvious for you? Uh, well, finitely many elements in a metric space may be open. We will see in a minute. It is not the reason, actually. Uh, you know, this is not open because if it were open, then we could find a ball around 0 that lies inside this set. But you see, 0 is this point, and if you take a ball around this point, then you would get something like this, radius r, and this ball clearly doesn't lie inside this set. Therefore, it is not open. Okay. Singletons may be open. Maybe not in this topology, but in some other metric space. We will see in discrete metric space, every subset is open and every subset is closed. Okay. Sometimes people say that this is not open because it is closed. That's not also a valid argument because a set can be both open and closed. Okay. This is not open because you cannot just find a ball around 0 that lies inside this set. Okay. Here you see that there is this point. There is this point. No matter how you choose R, there's always this point R over 2. This is inside the ball, but R over 2 is not in the set, right? Because it has only 0 in it, and R over 2 is a positive number. Does this make sense? Similarly, arbitrary unions of closed sets may not be closed. So this means what? This means hence arbitrary intersection of open sets may not be open. Similarly, arbitrary union of closed sets may not be closed. And here is an example. So this time let me give you example A and to B. Okay, so take this closed sets. These are closed because this is just a ball, right? With center 0 and radius 1 over n. This is a closed ball, and we know that closed balls are closed. So this is closed, which is closed. I mean, of course, in the standard metric, right? These examples for in the metric space are equipped with the absolute value metric. Okay, these are closed. What about their unions? Well, you see. So I take the union of these balls and n goes to, this is not good example. I should, okay, change this. Okay, so let me write it this way. 1 minus 1 over, no, minus 1 plus 1 over n, 1 minus 1 over n. Yeah, okay. Now it works. So what is this? Let me minus 1 here, 1 here. And this interval, closed interval, is the following. So this distance is just 1 over n, okay? So minus 1, I add 1 over n to that. I am here, and 1 minus 1 over n. So these distances are 1 over n, okay? And I take union. As n goes to infinity, what happens? This end points tends to minus 1 and 1. They cover everything except till minus 1, but not minus 1. And here this endpoint will go to 1, but it will never reach 1. Therefore, this union is just the interval minus 1, 1, and this is not closed, and minus 1, 1 is not closed. And this is not closed. Why is that? Because, if it were closed, then its complement would be open. Its complement. What is the complement? Complement is this: minus infinity 1 minus 1 union 1 infinity. This is not open. Okay. And why this is not open? It is not open because of the following. You see, I have this interval and this interval, and consider this point. If it were open, then I should able to find a ball around 1, and that interval, that ball should lie inside this interval, this set. But no matter how small you choose your ball, there is always some point here that doesn't lie inside this set. And what is that point in this case? So this point is just 1 plus r over 2, right? No, 1 minus r over 2. This is inside this interval, 1 minus r, 1 plus r, but 1 minus r over 2 is never inside r minus 1, 1. Therefore, no matter how small you choose your r, this ball will not be contained inside this union. Therefore, this is not right. Therefore, this is not open. Any questions so far? Okay. Okay, I was going to do examples, so let me make write down the following example. So let X be any non-empty set, and D be the discrete metric on X. So what was this? Remember, it was the following metric, right? Whenever you give me 2 points, I look at whether they are equal or not. If they are not equal, I say the distance between them is 1, and if they are equal, the distance between them is 0. All right. So clearly, you know, if X is any point in X, then what is this ball? With center X and radius, let's say 1 over 2. Well, this is the set of all points in X such that the distance from X to Y is less than the radius, which is 1 over 2. However, if this number is less than 1 over 2, then there is only one way, right? It has to be 0, because this matrix takes only two values, 0 or 1. And if it is less than 1 over 2, then it must be 0. But if it is 0, then we know that Y has to be X. So this set is the singleton X, okay? But this means what? So uh, the this set is a ball, right? It's a ball, hence is open. Open for any x, for any x in x, right? So every singleton is an open set. But if every singleton is an open set, then every set is open. Why is that? Now, if A is any subset, then A can be written as what? A can be written as the union of singletons, right? Take every element of X, consider this singleton, and take the union, right? This is just A. But uh, we just wrote A as the union uh, of a collection of open sets, right? Each singleton is open, and this is a union of open sets. Therefore, A is open, is an open set, subset. Since each is open. Well, so what we see is then any subset of X is open, right? But if any subset is open, then any subset is closed, right? Because every subset is the complement of another set, and that set is open, therefore the complement is open. Uh, Moreover, if let's say B is any moreover any subset is closed because A is just x minus A, and x minus A is just a subset, and we know that any subset is open, and x minus A is an open subset. So uh, we also know that uh, of course uh, X itself is open, right? The as a clearly as a subset X of X is open. Why is that? Because if you take a ball around a point, that ball will lie inside X, because our whole set is X, right? We just live inside X. There is nothing outside X. So any ball around any point lies inside X. Therefore, X is open. Since it is open, hence empty set, which is X minus X, is closed, right? If X is open, then its complement is closed. However, empty set is also open. Why is that? Uh, I'll leave this as an exercise to you, but the reason is clear. It is open because you see, if it were not open, then empty set would have a point, so that we couldn't find, we wouldn't find, a ball around that point which doesn't lie inside the empty set. But we cannot find such a point because the set is empty. Therefore, empty set is always open. And since this is open, hence X, which is X minus the empty set is closed. So in a matrix, in the discrete metric space, every subset is both open and both closed. So conclusion, in a discrete metric space, every subset is both open and closed. Also, here we of course uh, showed along the way, in any metric space, not necessarily discrete, in any metric space, X and the empty set are always both closed and open and closed. So in any metric space, the subset X itself and the empty set are both open and closed by this argument. However, in a discrete metric space, actually any subset is open and any subset is closed. Okay? All right. Do you have any questions? Maybe another example. Few minutes ago, one of your friends said a subset was closed because it is a finite set, right? Something like this. And that's true indeed. So uh, singletons are always open, closed. Why is that? So let XD be a metric space, any metric space. Then X minus little x, take any x, its complement is uh, open for any x. Why is that? Well, you see, my set is outside x, right? Anything except this point is my set. So if you choose a point, so let u to be this. If y is in u, x minus x, then of course y is different than x because y is here, so it is different than x. But this means there's a positive distance between x and y, and thus dxy is positive. So there's a positive distance between these 2 points. So let r to be the half of this distance, which is again positive. So I look at the distance. This is of course not the real picture, just a symbolic picture. If you take r to be the half of this distance, okay, then clearly the ball with center y and radius r will not contain, right? X will not be inside this ball. Sorry. Because the distance between X and Y is more than the radius. Therefore, X is not here. But this means, and thus, this ball lies inside X minus the singleton. So, what we have done is then, you see, I started with a point in Y, in U. I found a positive number so that that ball lies inside this set. This means X minus the singleton X, hence X minus this singleton is open. And since this is open, of course, thus this is closed. So every singleton is closed, okay? And we know that finite union of closed sets is closed. In particular, if x1, xn are points in X, then this set, which is just the union of xi's, I from 1 to n, is also closed. Because it is a finite union of closed sets. Okay, any questions? Okay. Now I'll talk about interior and exterior. We defined interior. Did we define exterior? I guess I haven't defined exterior, right? We defined interior, but let me remind you the interior definition. Recall that a point X in a set, let's say A, is called an interior point if what happens? If there is a ball, uh, B x epsilon. Of course, epsilon is a positive real number, so that A lies, X lies, of course, in this ball. It is the center, but this ball lies inside A. Okay, and we write this in this case. We write X is in int A. Okay. Şöyle yazayım. So int A is the set of interior points of A. So what is int A again? It is the set of all points such that there is some radius, positive radius, let's say epsilon, such that B X epsilon lies inside A. Okay. Okay. Here is another definition. For any subset, for any subset, uh, of course, XT is a metric space. The exterior of A is defined as follows. The notation is this: x of A, the exterior of A, and this is defined to be the interior of x minus A. Okay, so it is the interior of its complement. Right. So exterior is the interior of complement. Okay, and here is a fact, little proposition. Interior of a set is always open. Interior of A is always open. Why is that? Well, this is very simple because it consists points so that you can find a ball that lies inside A. Okay, so I can do the following. Uh, okay, now let X is in interior of A. Then there is some epsilon X positive, right? A positive real number. Let me write epsilon X because for each X I may have to choose a different epsilon. A common epsilon may not work for all x's. There is some epsilon x so that this ball with center x and radius epsilon x lies inside A. But then I can write this then uh, okay. Of course, okay. Now I claim this claim. Yeah, it is a little bit uh, okay. I have to say uh, some more than I would think. Okay, so claim is this: I have a ball like this, but actually every element in this ball is also in the interior. So claim is this: this ball lies in A, but actually it lies in interior of A. Why is that? Proof of the claim. If I draw a picture, it will be very immediate. You see, here is A, okay, and here is my, let's say, X, and here is our epsilon X radius, epsilon X ball, and what I claim is this: every point in this ball, every point in this ball is also uh, an interior point. Well, for y to be an interior point, what I have to do, I have to find a ball around this point that lies inside A, right? For y to be an interior point of A, I have to find a ball that lies inside A. However, if I choose this ball so that it lies in this big ball, then I am done because this big ball already lies in A. So that's the strategy. So what I uh, have to claim, this ball is inside in the interior. So let y be a point here. Okay. Uh, you see how I should choose the radius of the this green ball. The radius should be so that the total distance from this point to here should be less than epsilon x, right? This is epsilon x. So okay, let r to be epsilon x minus the distance between x to y. Okay, then uh, we have, from the picture we see that the ball with center y and radius r lies inside the ball with center x and radius epsilon x. Why is that? You see, uh, let's prove this. uh, because what is the distance between uh, because if, let's say, z is in this ball, then the distance between z to x, what is this distance? By the triangle inequality, this is the distance between z to y plus y to x. But distance between z and y is less than r, clearly, because it's inside this ball. And the distance between x and y is less than uh, epsilon x. Yes, sorry. Yeah. Mm, wait a minute. Distance from x to y uh, is less than distance between z to y. No, we have to be more careful. Sorry. Here is z. Okay. The distance between x and z has to be okay. Okay. Yeah. Now the distance between z and x, this distance is less than distance between z and y. Oh, Z and Y is what distance between Z and Y plus uh, distance between Y and X. Yeah, okay. Now distance between, okay, Z to Y is what? Uh, this is less than R because Z is here, so this is less than R plus X to Y, but R is epsilon X minus the XY, and I have plus the XY. So what we see is then, hence dZx, sorry, is strictly less than epsilon x. So this means so that Z is in the ball, Z is in the ball with center x and radius epsilon x, right? So I have seen that this uh, green ball is inside red ball, and the red ball lies inside A. Uh, so Z. So what we have seen is this. Z is in, of course. A. So I started within a point in this ball, and that point lies inside A. Therefore, this ball. So the ball with center Y and radius R lies inside A, which means that, which implies that Y is an interior point of A. So that was our claim, right? Uh, I picked any point from this ball, and we have seen that that point is an interior point of A. Uh, so uh, therefore, thus, okay, this ball lies inside interior of A, right? Because any point in the ball, any point in the ball uh, is in the interior. That's what we have seen. It's in the interiors. Therefore, this ball lies inside A. But this is exactly what. So this finishes the proof of the claim. My aim was to show that interior A is an open subset. Why it is true? Now, back to the original statement. Interior of A is what? Well, interior of A is what? It is the union of singletons, right? I can write it this way. Every set is the union of singletons. In our case, this singletons lies, of course, inside this balls, right? Every singleton in the interior contains a ball of radius epsilon x, which depends on x, but that ball lies inside A. Moreover, we just showed that actually that ball lies inside interior of A. So each of these balls lie inside interior of A. Therefore, their union will lie inside interior of A. Now let's see what we have obtained. I started the interior A and showed that it lies inside interior of A. Well, this is possible only if all these inclusions are indeed equality. This implies that interior of A is actually equals this. But this means what? Interior is a union of open balls. Well, each open ball is open, therefore interior A is open. And thus, okay, let me write. In particular, interior A is a union of open subsets, open balls, open subsets, which are balls, and thus, sorry, interior of A is open, is an open subset. Okay, let's see. Okay, I yeah, went a little bit too much, I guess. Let's stop now. Let's save 10-minute break and then we will continue.